Okay. Good morning. So today I try to use chalk on blackboard, and so that you can easily follow my lectures. So today I will introduce this amplitude analysis tools with this covariant tensor formalism. So first I will introduce to you the general framework for the amplitude analysis. General framework. Sometimes it's also called PWA, partial wave analysis. More general is just amplitude analysis. So this is very commonly used in the study of Hadron spectroscopy. We know the most general reactions for the study Hadron spectroscopy is that one beam hits the target, so it's a two-particle reaction, and then after the collision, they produce n particles, final state, like K1, K2, Kn. What the experiment measure is this full momentum of each particle. That's what the experiment measure with the detector. And the initial one is P1, P2. This is a most general process. So the hadron spectroscopy to look for new hadrons is trying to find what's the new hadron resonances found in these processes and reached this final state to try to find some new resonances. And another, sometimes not like this, then like LHCb, they first reconstruct one particle and then study the decay. For example, for this pentaquark with hidden charm, they got from lambda b decay to GF psi proton plus kaon. So first they reconstruct the lambda b. So they start not from at the beginning is hadron collision, but they use detector only choose lambda c. This is lambda b. Lambda b is long with long life and can run some distance and then decay to this. And so they separate this lambda b to study this one body decay. So another common thing is one body decay. K1, K2, Kn. So it's one body decay and two body processes. Most general reactions are like this. And from this we know that the formula to calculate the decay width or partial decay width distribution of this final states is something like this. M is the mass of initial particle, and then is amplitude squared, and there is d phi n, and that's the function of Kn. This is for the one particle decay to n particle final states. And for this there is also the d sigma, the differential cross section is proportional to the m squared. This is a theoretical, maybe I read too crowded, and I think you can follow this. It's for this, and okay. So this is just a phase space factor. It's kinematic factor, and the m is this invariant amplitudes is also the function of k1 to kn. The function. This is a theoretical formula, standard formula, listed in the PDG booklet. So this is a standard formalism for the two-body reaction and the one-body decay. So but experimentally, what you measure is each event you get k1 to kn. This you can select this final states, and the probability to find an event in this we call the experiment measured probability function k1 to kn. So it's no matter for the one body or for the two body initial states, this is proportional to m k1 to kn squared. And then there is another function, k1 kn, and then d phi n k1. So this is have this factor. This one is called the detector efficiency. Since the detector is not an ideal detector, can for every event for every direction can get 100% detector efficiency. For different K1 to Kn, the detector efficiency is different. So what experiment measured is this one. So it's the amplitude squared, phase space factor, and the detector efficiency. And to start from this, we try to, what we are most interested is try to get this amplitude and to get what's in for this amplitude. For the phase space factor, I think some of you maybe should already know. For the two body, not defined yet, okay. The definition of d phi n k1, the phase space factor, is equal to delta P is a total momentum of the initial state. The definition of this phase-space factor is like this. And this is for each final state. This, in fact, this comes from is equal to so this is a Lorentz invariant. So the phase space factor is a Lorentz invariant. All this is written in the Lorentz invariant form. And so this phase space factor is like this. Let me. Sorry. The delta. This is a on-share condition. You can get this. So this is a form factor, and commonly used. Sometimes we say two-body phase space factor. That's just a okay. I give the simple example is D phi 2 initial is P. This is I think but I should give this. For this, if in the center of mass system, this P equal to some invariant mass, they in the center of mass system, then you can integrate this delta after integrate over delta. Then you will get. It's very easy to do this, and you. At rest system, there is a K1 equal to minus K2, and this is a K1. This is this angular differential. This solid angle. If you consider no angular dependence, you can also just integrate over this. There is this replaced will be replaced by So this two-body phase space is just proportional to the breakup momentum. Maybe I should, here I should use this Q. This is the final state relative momentum. So this is quite commonly used. The two-body phase space is just proportional to the relative momentum. This is when people say the two-body phase space is like this. Q, okay, Q, yeah, this is just a Q. It's a relative momentum. It's the center of mass momentum. Let me 2Q. Let's assume this this equal this equal to this, and if for the same mass final states you can get the Q equal to this K, and you can get this. It's for parent particle at rest system, and the final two particle is have opposite direction, and for the same mass they is equal, and this is what I call it. Maybe still keep this K1 to not to make you confused. Okay. So this is a basic formalism for this relation between the amplitude and the observed probability function. And then for two body it's like this. For three body, you can also similarly get this. If initial states have no spin dependence, then you can get so-called Dalitz plots. They will only depend on and so-called Dalitz plot analysis for three body. If the initial state is spinless, or you just sum over all the spin projections, then you can get so-called the Dalitz plot distribution include all the information. But generally speaking, what the experiment measured is a K1 to Kn, this four momenta for all particles. That's what the experiment they measured directly. You should remember this. So, then is how to after you measured this, you can make the projections. If you integrated some variable, then you can make all plots with different, you can keep one variable not integrated, then you get the projection to that one, get all the mass plots, invariant mass plot, or momentum plots, every projections. But all the information is included in this distribution measured this. And then is how to construct the amplitude, how to extract the information for resonances. And this include many sub-processes, like may produce some resonance, and then it decay. And this is R1. Then it's also possible you have some R2 and whatever possible resonance there. Then you should then you get this amplitude. It's just the sum of the amplitude for R1. So you can think about all possible sub-processes and to rate their amplitudes. And these amplitudes will have some unknown parameters. That's the parameters to be determined by fitting to the data. Yeah, C1, C2. And even within the amplitude, sometimes you have the mass and the width not known. And that can also be parameter to be fitted to the data. Yeah.
Sorry, so very but resonance shows up as like a spike in your like plot in terms of like a area or something. How do you see a resonance in an experiment?
Yeah, that's a good question. But first, let's assume it's just a resonance. It's possible not resonance. Then you should think about how to rate the amplitude. But in any case, for each sub-process, you can construct some model amplitudes. You may use amplitude, you may use not amplitude, but other parameterization. You just rate whatever you think is possible for your amplitudes. Here may be resonance, but may be non-resonance. Then you rate other possibility. Then to fit to the data to see, first you should get something fitting the data. If your model cannot fit the data, then your model is not correct. You should find some other possible solution to fit the data. The resonance is a simple assumption, but it may be, as you said, how you prove is really a resonance. That's another question. But at least first you can construct possible amplitudes with parameters. And the amplitude analysis is just try to use these amplitudes with parameters to fit the data and to get these parameters. Yeah.
So these amplitudes A1, A2, these are known?
Yeah, it's with different, for different resonance with different spins and different properties, we can rate this amplitude. I will show how to construct for various cases this amplitude. There is some regulation to construct this, and this is known amplitudes, maybe with also with some parameter. So besides C1, C2, here also maybe have some additional parameters. All these parameters should be determined by fitting to the data. You try to fit the data, get this amplitude, then compared with the data, should describe the data reasonably well to make it is a possible, acceptable solution. Sure. If yeah, that's possible, multiple solution or something. But sometimes it's not so easy to fit the data, even difficult to find one solution sometimes. Yeah, it's possible you find several solutions, and you need to judge which one is more maybe you have two solutions. With your model, you can make other predictions. The two solutions will make predictions to other, then you check by other processes to get rid of one of them. Then you get the unique solution. Maybe you combine the fit to solve this problem, multi-solution problem. Sorry? In principle, you can put whatever you need, enough parameters to fit. But you should construct a reasonable model, not with hundreds of parameters. If I can fit the data by one parameter, definitely you'll find some model with 10 parameters, definitely can also fit. Yeah, but we try to construct the dominant amplitude to fit the data. So the old-fashioned fitting is to fit the projection. Each projection, we can make the integration and to fit the projection to so-called chi-square fit to various plots. That's old-fashioned, and they also lose a lot of information. Now the most advanced fitting is so-called event-based maximum likelihood fitting, the so-called event-based multi-dimensional maximum likelihood. Event-based multi-dimensional maximum likelihood. That's we do not make any integration. We use all the information. That's the information of each event, and for each event, you measured the form momentum of each particle. All this information we fit directly to get this, no integration. And by this, in fact, this is just use this theoretical formalism to fit this W exp k1 k2 is to kn. Oh, here is should k kn to fit this directly. That's the event-based. So all the information measured are used, not a single information dropped. So this is the most advanced fitting. And this, you don't worry about how to do it. It's already have this computer program, this standard package. And at the third leap, the developed at the third leap is the family called subroutine family, and minuit. This two program as commonly used two program. So what you input to this subroutines is this function of K1, K2 of this, what you input is all this M you need to put in the subroutine for this function. And then from an experiment, your input is for each event, all the form momentum of all particles. So it's directly all the information involved to then this program will help you to find the best solution. Yeah. So this is a general framework for the partial wave analysis. It's a standard way. And so for physics analysis, so okay, same. So now the problem is the construction of covariant tensor formalism. So the problem is how to write all these amplitudes. That's the first part. Okay. Now you should put the first part for that. There is a construction of PWA covariant tensor amplitudes. This formalism is not new, and I can list some references for you. The first one is Rarita. This is sometimes called Rarita-Swinger covariant tensor formalism. So it started from (1941). Physics Review. And the Fujip side, what we this for me sounds and there are many others you can find in this. We also list some relevant references there. You can find more references. I like this formalism is because it's construct from the full momentum of each particle. Another commonly used is helicity formalism, and Professor Chung used to use helicity formalism, but this paper he's trying to get the helicity amplitude from covariant tensor formalism. This covariant tensor formalism also gives the momentum dependence there. And then I asked Chung why he still use helicity formalism not instead of covariant tensor formalism. He said all his old program is written with helicity formalism, and he want to keep use that, so he used the covariant tensor amplitudes to get this helicity amplitude to fit to the data. So it's basically the same what he used. And for me, since I starting from covariant tensor formalism, so I used to fit the data, just use this covariant tensor formalism. So to construct the covariant tensor formalism, there are several basic ingredients. Basic ingredients. One is a spin wave function for single particle. The second is a orbital wave function for two-particle system. Since we know that for one particle, the only wave function is a spin wave function. Of course, for one particle, they have the momentum, but when you're talking about momentum, you should relative to some other things. For at rest system, the only wave function is the spin. And for the two-body particle, besides spin, they should have the relative momentum distribution, different angle. So it's an orbital wave function for two-particle system. And then the third component is such Breit-Wigner propagator. And the form factor. So they are basically just very simple. Just use this to get to construct the covariant tensor amplitudes. Oh, it's getting very hot now. Here is really warm. Yeah, yeah.
One particle to particle refer to the initial system.
To describe one particle, no, not initial, it's final, any system. Okay, it's also possible for the initial state. Just to describe the state. If one state with only one particle, then how do you describe this system? At rest system, the only wave function of the distribution is about this spin, whether it's a different projection, total spin and different projection. Then for two-body, then you have the relative momentum of two-body. This is generally speaking.
If in the final system I have 10 particles,
Yeah, okay, yes. Usually when we write it, we first construct two-body, then to combine with a third particle, and by this kind of things. But the ingredients is only one particle with spin wave function and two-body with this orbital wave function. So for gauge invariant. This is not really talking about gauge invariance yet. Of course, when you construct the amplitude, you should satisfy gauge invariance requirement. If you have the like a gamma or something, there's an electric magnetic interaction, you should satisfy. That's when you construct amplitude, you should consider all the requirement of the conservation laws, and also like gauge invariance also, any other necessary constraints you should consider. But to describe this system, the wave functions, how to describe these states, these are basic ingredients there. So now, first is a spin wave function. I think most of you, okay. Today, I first only talking about this meson with integer spin, and maybe someday later I will talk about the fermion with half spin, 3/2 or something. But for the first about this simplest case, that's for mesons. The spin 1, I think most of you know about this, is the spin wave function is just a polarization vector. It has spin 1, then it has 3 possible projection. That's we usually use this this covariant for vector for this. For phi, usually we write phi m. M equal to 0 plus 1. And at rest system, I think, I should, yeah, okay. At rest system, and you have I think most people know this. This is this time component, and then this space. Oh, sorry. So this is commonly used for the vector, and then for spin 2, it's also very easy. For spin 2, then you need this and this can be construct from since you already have definition of this and this, you can easily get this spin 2 wave function. This is just a CG coefficient. And this is for at rest system. And for any other system, you can easily just by Lorentz transformation get to any frame. So it's straightforward, and just continue for s equal to 3, and to construct one by one, you can construct all of them. For the spin wave function, that's very simple, very straightforward. And okay, some useful properties for this is first is this orthogonal condition for any rank tensor of this particle. Since this P is the particle at rest system, P is just the mass of this, but you can get to any frame, and the P can be anything. Then this contracted with this is equal to 0. Yeah, that's this so-called perpendicular condition. You can easily check this, starting from the first one. At rest system, this P is this is M and other 0, so it's no problem. And then for any system, since this is a Lorentz invariant, this is always satisfied. So, and another useful formula is this symmetry between different vertices. The second, when you make the calculation, this kind of symmetry and the condition help you to simplify the amplitudes. And another one is equal to 0, the condition. Oh. Okay, I will continue to this, but I think you already get this, and oh, maybe Now is a good time for some break of 5 minutes. Okay.
Like
但是它的辐射你在做投影，一做投影这个更容易监督，所以这个成本会提供更具体的。你如果是连中文的都用，连做投片，它们所有的投片都符合。 对，实验室就是，所以这是你们的 base 基本上都是在自己实验室里，他就必须知道这个，他探测器的这个，他一般他不会额外的，比如说他这个各种探测器，他这些图片除非是他做给投影，可以做效率修正，把这个效率修正给去投影是可以通过效率修正之后，然后再包括对实验的都可以说。 效率修正之后，但那样的话，你拿到的只是部分信息，就是投影后。当然，就说你如果是你和那种的，可以直接相当于把这个当成一的，因为它那个当成修正后，是你和那个。 Okay, let's continue for this. Some students ask how we get this. Yeah, I think look at the reference they may show, and yourself may also prove this are valid relations. Otherwise, you can just simply use this, assume it. If you suspect them, then you should try to see whether you can find anything violate this three relations. This is a so-called no trace condition, and this is perpendicular to the its own momentum, and this is this exchange symmetry. And after you get the spin wave function, then it's a useful formula is a spin projection operators. I think for the spin half, yesterday Professor Craig Roberts already showed. And for the spin one, I think many of you should also know this spin projector. This is very useful for this spin projector. When you write this Feynman diagram, you will always have this different spin. You will need the sum over the different projection of the spin, and then you will get this spin projector. So it's commonly used for the property. And for the spin one, spin projection propagator is just the particle momentum. I think most of you know this. This is for spin 1 projector. It's like this. And then spin 2. In fact, from the formalism there, you can prove by yourself to get these projectors. For spin 2 and for spin 3, similarly, all these projectors you can get from the references already worked out, so you can just use it. For you to use, it's not necessary all of you to just get how to deduct this formalism, but the theory papers already give explicitly for all these projectors. For it's just mu lambda, and then mu prime mu lambda prime, and for 3, and with 4, all this can be expressed as some combination of these things. That's a useful formalism when you get these amplitudes. That is for one particle. For one particle system, the only invariant, the variable to describe them is the spin and their projection. So the spin wave function with the spin and the projection m, you can get this wave function for this single particle. And then we come to for the two particle system. Besides the spin wave function, then we need to know the orbital angular momentum system, and that's a spin wave function. Then we have this orbital wave function for two-body systems. Since like for one particle decay to B plus C, two particles, we want to describe this final state. If we for this system, there is first the total momentum should be equal to this momentum of parent particle. And then the only variable is this R. Right, that's the relative momentum of the two particles. It can have different, for fixed mass of ABC, so this basically describes this angular distribution. Since the magnitude of R is fixed, but which direction you don't know, so the basically is the angular momentum is described the orbit, this angle distribution of the final state, probability function. And this is also what if for the relative orbital angular momentum to be L, then its wave function, the tensor wave function, what we used is this. It's straightforward. It's just this projection operator. Then contract with this relative momentum like this. And this is a so-called centrifugal barrier form factor. This is how to say this? Sometimes people do not write this. This is just depends on this. The QABC is the breakup momentum. That's A decay to B to C. So it's at rest system, the relative momentum of B and C. This is this. This this is a so-called centrifugal barrier. That's because it's a hadron have fixed size. This otherwise, okay. Maybe first you just remember it's a form factor. Later on I will show what's why we need this. But basically, the major part is this part, and this describe the wave this relative orbital angular momentum distribution. Why is this? I show you a simple example. Let's try first the L equal to 1. If L equal to 0, then it's just a constant. There's no special direction. It's a spheric symmetry, and it's just a constant. Then let's consider the lowest one, L equal to 1. What happened here? If you what is T1 is just is mu, and then is equal to the first projector is there. So it's just G mu prime minus then so it's basically about this. First, let's forget about this centrifugal barrier factor. Let's try to make it not go to infinity for very large R. That's to reduce this, to make it converge for the large Q. And for this, what's this? If you, to simplify things, let's assume this MB equal to MC. Then sorry. Should consistent here. So this is equal to R mu, and then is to make things simplified. This is just this is PA times PA minus PB. We know P mu is equal to PB plus PC, and R is, sorry, I confused. This is equal to Ka. K. Since P equal to Kb plus Kc, and R equal to Kb minus Kc, so this two is just like this. So it's equal to Mb squared minus Mc squared. Let's first try to, in the case Mb equal to Mc, this is just a 0. So let's consider the Mb equal to Mc. So this is so the wave function is basically just this relative momentum. This to describe the two-body system, the only variable is this relative momentum. If you know relative momentum, you already know everything. So this describe this orbital distribute this movement part. It's just this relative momentum. In fact, it's easy to understand. In fact, in China, in Beijing, for our institute, we have if you want to go to PhD study, we have an entrance examination. And one problem I said is for the phi meson. Phi meson, I think you know, is a spin 1. And in Frascati, a lot of phi is produced, and the phi can decay to k plus k minus. And my question is, the phi produced from E plus E minus collision, we know that is polarized along the beam direction. And I ask what's the angular distribution of the k meson relative to this. That's my question. Just we know the phi, for example, polarized. So it's spin equal to 1, and also the projection either plus 1 or minus 1. The 0 is not allowed. Then if the phi is polarized in the state spin 1 and m phi equal to plus 1, what's the angular distribution? And after so many years, not a single person can answer in the exams for this simple question. Yeah, but in fact it's extremely easy. I'm not sure any people know the answer here. If you know, you raise a hand. It's very simple. There is anybody want to try to give the answer? It's in fact, it's very simple. First, the total spin is 1, and the total spin projection is plus 1. That's the initial state. From the momentum conservation, the final state should have J equal to 1. For the final state is just this. Should J equal to 1 and Jz equal to 1, plus 1. That's just conservation law. And then, for the final state, the two-body wave function, that's the only angular momentum orbital part. Then, no spin for the final particle. So the final state should be L equal to 1, Lz equal to plus 1. So the distribution probability, just their wave function. The wave function for this relative motion is just y11 theta phi. That's the wave function for this L equal to 1 and ML equal to 1. And the probability is just the squared, the probability distribution. It's just this. And this is just proportional to sin squared of theta. That's the answer. The distribution is like this. You should know how the normalization. So it's just from the conservation, from this, if you know the wave function, know the conservation law, you can have this. This is without learning any such things, you should be able to get the result. But if you know this, you can also easily get from this formalism. Then, from the formalism, this is phi spin 1. Contract with T, maybe T mu 1 for this R. So this is just the amplitude. This the spin and contracted with this, then you get this and you have there like this, like that. So it's a should be no. Rx, Ry, and this is just if you plot this, it's just y1. Besides this, you can show that is y11. So you from this formalism, you can also easily get this this tensor like this times this spin 1 projection. Then you just get this y11 distribution. So, sorry? Rx. Oh, yeah, sure. Yeah, it's plus, yeah. You're right, yeah, there is a plus, yes. And you get this y11. So, sorry? Yes, this. Yeah. Okay. And we know that m is proportional to this, and from the initial state to the final state, and you can get this, and you can also get just the angular distribution is just y11 theta phi squared with just quantum mechanics, the conservation of the momentum. I showed you how to get it. Then from this covariant tensor formalism, you can get the same result. So it's also straightforward. Okay, so this is so now you know how to construct the spin wave function for a single particle. And for two particles, it's just the sum of the two spin. And then for spin part, is straightforward. You just have the spin for each particle. Then you have the relative orbital angular moment for orbital wave function. You have this for different L. You can have this kind of wave tensor, covariant tensor wave function for each L. After you know this, then you just need to construct effective amplitudes, the covariant amplitudes. Then you can get the the general M, the amplitudes, invariant amplitude for whole processes. Just like similar to the Feynman rule with the propagator and with each vertex, the couplings. I will show you some example. So this. Okay. So now I come to examples for one body, one hadron decay to two particles. Examples. First is one body decay. Or maybe just A to for various cases. The simplest case is F0 to pi. That's the most simple one. This is no spin, and when this is both no spin, then the angular momentum of 2 pi definitely can only be 0. So no orbital angular momentum, no spin. The amplitude is simple. It's just a constant. It's just a constant. So you can, if you write here, F for sigma is the same. It's just a constant. And then how you get this, if you know this constant, then we know you can use the two-body phase space factor. I don't know what the previously I showed you the formula for this. The gamma equal to and for this is just a constant. The relation of gamma and the coupling constant is like this. So from the experiment that you observed a peak for this, and you get the width, then you can get the coupling constant here. Then later on, if you try to study different processes like this, you can easily write this G sigma F pi squared MF after you know the one-body decay width, then you can get the two-body scattering through this resonance. That's the most simple case. And the second case I already showed you. This, in fact, the two-body decay. So I will not go through this. Let the second rho decay to pi. This is also straightforward. M equal to just G rho pi. And then rho mu. Rho is just a spin vector for rho. Spin just as a phi. You can write the phi. For vector I write the rho for rho vector I just write rho, and you can easily get this. Let me think. And this is basically just equal to R mu for pi. And you can, after sum over of this, m squared, just equal to, when we write this, which means m equal to 0 plus or minus 1 for this, and the sum over, they should be divided by, to get the average for this. It's just and then with this, you use the previous formula for this width, similar to that. Let me see. Or maybe, let me think. You need to work out what is maybe some factor here, but you can get this, and from the decay width, you can get the rho coupling to pi. Then you get the constant, and for all other processes, you can just use this. The sum of, let me try to show how you. I think you should know how to get this. It's just then is sum over this. It's just R squared. This sum over is G mu v. And with this, you know the R, and then you can get this rho squared with the formula. But here, in reality, sometimes you need to also consider isospin. I haven't put isospin here, so you should pay attention to this. Depends on your definition for this. You can, if you have the rho 0, pi plus, pi minus, directly you can get that one, and you can get for each charge state. You can also get a common one with additional isospin factor if you want to keep the isospin operator there. For isospin part, it's similar as spin part. It's just in another coordinate space. Yeah. I'll give you some more difficult example. The third example, omega to rho pi. This is also a common one. And anybody want to try to come here to show how to write this one? Volunteer. You already have all ingredients, and should try to write this. Okay, maybe no volunteer. Okay, you come. Yeah, good. Very good. Yeah. Rho is spin 1. Yeah. Yeah. Omega is spin 1 also. First, you try to see what's the orbital angular momentum. Orbital angular momentum is between two particles. It's for two-body system. So you should consider for the rho pi whether they should have angular momentum or not. It's fixed. It's the omega is. It's not like this way. First, you need to consider the parity conservation. The omega is 1 minus. Rho is also 1 minus. You should, I think most of you know the quantum number here for the GAP. So it has to be equal 1. Yeah. So L can be only equal to 1 to conserve this parity and also conserve the total angular momentum. L can only be equal to 1. Okay, I think this maybe is too difficult for you. I should find some simple one for you. But this is another problem here. First, this is 1 minus, this is 1 minus, 0 minus. L should definitely equal to 1. Then these two should construct to the total angular momentum should be equal to 1. Then how to yeah, so if you contract this with this, then which means you contract this to be scalar. You must construct it to be a vector. Since spin 1. Yeah. So you should try to make them to form as totally should be the Lagrangian or the amplitude should be scalar. So you should construct with these 3 parts to get the scalar. In this case, is 1 coupled with 1 should equal to 1. Then you must introduce another. I think. Oh, I already removed that. Then you must use this one. This is for construct 1, 1 to 1. So this m, in fact, is equal to, if this is a p, the momentum is p, and then it should p mu and omega v rho lambda t T1 sigma for this. So they can construct this G omega rho pi. Yeah, quite good. It's not easy for, since this needs to introduce another one, yeah. Omega is spin 1 for omega wave function. It's spin 1 vector. Yeah, omega is a spin wave function for omega. That's spin 1. So you need a polarization vector. And rho lambda, rho is for the spin vector for rho. And then there is T1. Then you need this 0 component for the P. Since for spin 1, we know the spin 1, the spin 2 also angular in the non-relativistically should be phi 1 cross phi 2 to get a vector. This if you form 1 1 to spin 1 to get the total spin 1 is a cross, and this is in non-relativistically it's just phi 1 phi 2, and to get the total phi k is by this way. When you for relativistically, then you should add 0 components, and you should put a thing here, but okay. In fact, here is as I showed, it's just the R. It's maybe not R. Okay. Let's still use this T. Okay. In fact, you can simplify by this. This can be, we know that if any two particles, same momentum appeared here, if you have one P here, then have another P around here, since this is a total symmetry operator, this will be equal to 0. So you can replace this by some others, like they will get the same. There is only one possibility for this, is a combination. You can not write, this is a PR. If you write something like this, you can also just write, they will be equal if you just use K1 and K2. Since this K1 plus K2 and this is K1 minus K2, and when they are same, they will be 0. So you can easily replace this by K1, K2. Then with this omega mu lambda, just this covariant tensor formula means you can get a unique. This is only one LS scheme. You can, for other decays, sometimes you can get two independent, let me think, two different amplitudes. Depends how many possible LS coupling. Maybe I give you some other example. This, since it's only one possible L, you can only have one covariant amplitude. But sometimes you can have S wave and another is a D wave. Then you have two possible amplitudes. You can use this covariant LS angular momentum to construct this. But today we just showed some simple examples, but all others you can construct similarly with the ingredients I listed today. Yeah, maybe since time is nearly finished, so I leave 1 minute for questions.